two ways of doing this. Okay, continuing with lecture 10. And I will tell you, so tomorrow I'm going to be out of town. We got a grant. We have a grant, yay. Only it's not for engineering, it's for computer science. We got a grant. We're part of a consortium that got a grant in the Bay Area to develop a mobile app development program. So people can do mobile apps here someday. We're going to share all our resources and curriculum, hopefully, and it will be a certificate. It's one of those things that there's a lot of, the state of California recognizes there's a lot of demand for this. And if they could get people with these certificates, they can probably get jobs right away and help fill a need that's out there.
What do they use for that? Java usually for mobile apps?
Yeah, Android is sort of a Java thing, and iOS is sort of a C++. It's Objective-C.
Okay.
Yeah. Yeah, so, but we are really short-staffed. So I'm going to be up at the meeting. Matthew Kyler is going to be here tomorrow. There's a quiz tomorrow, so it'll be a problem session. We can work with each other. I'll have him. So what's due tomorrow? Assignment 9 is due tomorrow. So if you're still working on assignment 9,
Will the quiz be online?
the quiz I'm pretty sure will be on first order circuits. I'll think about it. I'll send you an email out tonight.
And are you going to have a link for taking it online?
Yeah, if you can't make it, you can always take it online. I think most people would prefer to take it in class. And yeah, so and then looking ahead at the schedule, our next test is in is it 2 weeks, something like that?
Next Friday, right?
Is it next Friday already? I think it's the Friday after. So this is the here. So yeah, we have a quiz this Friday and next Friday, which I think that's second order circuits quiz, or maybe it's phasors, I don't know. And then, yeah, and then the actual test is on the 9th or something. So 2 weeks. Anyway, we're picking up with phasors and phasor domain analysis. And we did example 8. And the basic pattern is, anything that you could do in DC circuits, you can do in AC circuits. And it's just got to use complex numbers now, right? So our steps in solving circuit problems are generally the first thing we're going to do when we see a circuit with a sinusoid on it is we're going to have to calculate like the impedance of the circuit or the impedance of elements. So we calculate the impedance, which is the complex resistance of the inductor, which is defined as j omega L. And we calculate maybe the impedance of the total circuit, which is R plus ZL, which is 4 plus J, 2J, when you plug in what omega and L is. And you convert your signals into the phasor domain as well. Those become complex numbers. So your signal's a complex number. Your circuit elements are often complex. And then you just do your same DC analysis. This is the beauty of it, right? So we get to review everything we did already. Meaning if you did bad on test 2, the final exam is going to be hard because you got to do it all over again in complex numbers. So you want to make sure you master those things. And everything we do. So you can do voltage dividers in AC circuits. You can do current division, circuit reduction, like source transforms, Thevenin equivalence, and Y delta transforms also work as well. So we're just going to do, I think, 1 or 2 more examples. Example 9 and 10. And you'll see it's going to get a little bit messy, and then this will sort of lead us into next week. We're going to rely more on MATLAB's scripting capability to be able to deal with more complicated circuits. We'll actually start writing little programs to solve the circuits. And here we are with a circuit problem, and we're asked to determine the input impedance of the circuit below at omega equals 10 radians per second. So this is nice. We don't have to solve for any voltages or currents. We just got to find the equivalent impedance, series and parallel combinations, right? And what are we going to do? What steps are we going to use to solve this thing? We have a C1, a C2, an L. So we're going to do a transfer into the frequency domain, right? So our first step is going to be, let's find out what the impedance are of these different devices, right? So the impedance of a capacitor is minus J over omega C. And I don't know if you were here yesterday or not, but I'm asking people to add those to your LC table. You can do that at the bottom of your table. It doesn't really have anything for impedance. I should add that, but I haven't. For a capacitor, the impedance of a capacitor is minus J over omega C. And you just plug in omega and C. So C1 is 2 millifarads, so it's minus J over 10 times 0.002, which gives you minus 50 J. And ZC2 is minus J over omega C2, which is 4 millifarads, so that's minus J over 10 times 0.004, which is going to be minus 25J. So one rule of thumb, basically, you'll know is a capacitor impedances are always negative. And ZL, what's the formula for the inductor? Just to kind of start memorizing those things. They'll become second nature after you do a few of these. J omega L is the impedance of the inductor. So it's J times 10 times 2, which means 20J. Interestingly enough, they are all about the same order of magnitude. The capacitors and the inductors, 20, 25, 50. It will be interesting to see which one dominates. They're about the same, but and what we got to do is we're going to do the series and parallel combination of this thing, right? So what are we going to combine? What can we combine? Some people still have issues with these kind of circuits. What do we do? What's in series? What's in parallel?
The inductor and the resistive is in series.
Uh-huh. So this is one thing kind of some people do. They make big circles around the nodes so you can kind of see them better. I don't know if that helps you, but you can kind of see that you're visiting these nodes, these three nodes in succession. So these guys are in series. Also, these guys are in series, right? Some people also like to just sort of say, okay, well, this is one series combination, this is one series combination, and this path is in parallel with this path. Right. So you might start by saying, okay, well, this maybe we've got these two guys. Let's call this lump sum here Z parallel. And so far, so good. Z parallel is going to be the parallel combination of ZC2, which is the impedance of this capacitor, and this RL combination. So it's ZC2 in parallel with ZL plus 50. And ZC2 is minus 25J, so it's minus 25J in parallel with 50 plus 2J. And using the parallel formula with complex numbers, that's just minus 25J times 50 plus 2J over minus 25. Well, let's just do it. We're going to add all those things, right? Minus 25J, I'll just write that. Minus 25J plus 50 plus 2J. Did I mix that up? It's 20J, not 2J. Sorry. So again, this is something, it's not so bad if you have FreeMat in front of you or a calculator that can do complex numbers. This turns out to be 500 minus 1250j over 50. Darn it, I lost that. There's a 20j there again. Over 50 minus 5j. So we reduce this, right? We do the complex conjugate, 50 minus 5j, and, oops, 50 plus 5j, 50 plus 5j. Question, Willie?
Yeah, is that a 50U?
No, that's a 500. That's basically minus 25j times 20j, right? Because minus, well, wait. No, is that? Can't do any math anymore. So 50 times minus 25 is your minus 1250j, right? And minus 25j times 20j, yeah, it's going to be minus 500j squared, right? And minus 500j squared is 500, right? Going so fast. And then, so we're doing the complex conjugate to get the denominator to become real, right? Because it's kind of weird to have a complex number in your denominator. So we multiply by the complex conjugate of the denominator divided by itself. So we have the same expression. And what happens here is we have 500 times 50. So that looks like, should be, well, just to kind of cut to the chase, the total thing is 31,250 minus 60,000j. Over, and this thing is going to be 50 times 50 is 2,500, and then minus 5j plus 5j is 25, so that becomes 2525. And that equals 12.37 plus or minus 23.76j. Probably more, this will be more computation with complex numbers than you've ever done, I bet, in this assignment.
Conjugate, I don't think I've used the conjugate since algebra 2.
Yeah. Yep, so, but that's just z parallel. We also have to find z total, or z in. And to z parallel, we have to add the series combination of this guy right here, these guys, right? We have to add these guys to our parallel combination. So z total is going to be z parallel plus zc1 plus 20. And that's going to be 12.37 minus 23.76. That's z parallel plus zc1, which is minus 50j. Oops, let me just write minus 50j plus 20. And that gives you basically 32.37 minus j 73.76. The significance of that, I mean, right now it's just a meaningless complex number, and you're just trying to find a meaningless complex number. But this does have significance when we look at power transfer. We'll see some really interesting things that happen with these things. For now, we're just trying to calculate these complex numbers. But what this means is the fact that it's basically the complex, I mean, the imaginary part is negative, means that the capacitor is sort of dominating. It's a capacitive sort of load, because capacitors have a negative complex impedance. A negative impedance. Yeah.
And asking a question that's not really about solving the problem is we use complex numbers so we
don't have to use trig? Is that kind of the reason?
It started off that way, but it's becoming its own thing because there's so much more you can do with it, right? I mean, we started introducing complex numbers. That's a good question. I mean, we've gone and done all these things now, and it's like, well, okay. At this point, we're so far deep. I don't know how you could do all this stuff, like if with just trigs identities, right?
So at the start,
At the start, it was basically we introduced complex numbers as this nifty way to manipulate sinusoids, right? If you want to add sine waves together that have different phases and amplitudes, you turn them into complex phasors. They have to have the same frequency, right, for that to work. But when you do that, then you can just add the complex numbers and then do the inverse transform and get back to a sinusoid again, bypassing all the need for these complex trig identities, right? But those things are so nice that you know we've developed, and I can scroll back a few slides just to kind of fill in what we've just sort of been doing. Yes, because initially we were just transforming, maybe doing some addition and subtraction. We did that in the lab. But you know, when you start looking at, well, you know, if we're going to try to solve VO of t using differential equations, again, that's going to be a really tedious operation to do that. I mean, we could, just like we did for the step response, but it's going to be more of a pain. And so it turns out that what we're doing now is we have found, we had to sort of figure out, well, what happens to R's, L's, and C's then when you're hitting them with these sine waves. And we kept that phasor representation to kind of just play around with, well, what happens if we use, instead of a V of t on a resistor, we use a phasor? Well, with a resistor, it's still basically Ohm's law, V equals R times I. But with inductors and capacitors, when you do that derivative, we were working with sinusoids here, but we found, you know, with the phase change and going from sine to cosine, that we could actually, if we're talking about the phasor domain, we could actually represent this inductor law, which is this V equals L di dt, is expressed in the phasor domain as just basically V equals j omega L times I, right? And at that point, we've kind of left the trig world behind. I don't think we could even express this in terms of trig. You kind of have to use these complex numbers. But that J means that there's a 90-degree phase shift. So ELI, as Brock said, means voltage, which is electrostatic potential, leads, for an inductor, leads the current. And meaning we're getting a 90-degree phase shift across the inductor, so the voltage is going to peak 90 degrees before the current does. And the same analysis can be done with capacitors. So V equals minus j over omega c times I in the phasor domain, meaning the voltage is lagging, or current leads the capacitor, ICE. Eli the Iceman, is that the idea? So, and then, you know, this is the whole thing. Now, as I mentioned, these you can imagine these phasors are rotating at a speed of omega, because the phase keeps growing, and these two phasors will be sort of rotating around and around and around. There's another really cool animation I'll show you. I've got to get these animations working because it's nice to visualize these things.
Yeah, that's kind of what I was.
You want to see an animation?
Kind of the basis of kind of what I was asking, because we learn complex numbers pretty early, but we never really decide kind of like, all right, this is how you do conjugate, this is how you equal I squared, or I cubed, or I to the fourth, and I've never really gotten that. Like
yeah, you can't graph them or anything like that. It's kind of
You don't have an intuitive feeling?
And now we have something where we use it, and I think it's interesting.
Yeah. And this actually is kind of looking ahead, and I'll show this again. But it shows you the phasors going, which is kind of nice, right? And basically you have a voltage source, an AC voltage source, and it's showing you that the current, here's a voltmeter and a current meter, that they're in phase, right? Because you're hitting it, you've just got a resistor here. And the phasors are rotating, but they're in phase. Phase difference is the same. In other words, we're still representing V as a phasor, but the initial phase was 0, and it remains 0. I mean, it's really hard to talk about, when you, let me reset this thing. See, when we start, right, the initial phase on these things is 0. And they, migrate on their own. Now, if we just have a capacitor, we might say, let's see, which one's blue? Blue is the voltage potential, and I is the current. Current leads the capacitor. The phasor for the current is 90 degrees ahead of the phasor for the voltage. If we call 0 the reference phase for the voltage, the phasor phase is going to be 90 degrees. And that's at time 0, right? And we use these if we're given that the circuit says, V equals 24 cosine of 10t, there's no phase there, right? It means that the phasor is right there. And when we have multiple signals, multiple phasors, they may have different phase angles, and we're talking about where these arrows are at t0 before we start the simulation, right? And then once the thing starts, you can imagine them rotating, and what we're seeing as a sine wave is the projection of these guys onto either the vertical or horizontal axis. In this case, it's a little misleading because they're projecting it onto the vertical axis, where in fact our projection's on the horizontal axis because we're doing cosine. They're doing the sine here. For power, it doesn't really matter. But you can see that the voltage is peaking. In this case, the current is peaking 90 degrees before the voltage. You see that? And I'm jumping ahead, but this is a nice animation that I know you can kind of visualize that, right? But with the inductor, it's coil. The inductor has the voltage leading Eli, right? Voltage leads the current. So when you start this thing, it rotates like that. Now, again, it seems a little bit arbitrary, but there is significant meaning between what happens here, especially when you start thinking about power. And we're not going to look at power until next week, or even a couple weeks, I think. And then when you combine these things, you have some, now the total impedance of this circuit is something different. And the phase is, the current is leading the voltage, but it's not 90 degrees anymore because we have an R in there as well. It's like the impedance of that whole network is R plus ZC, right? And that means you have some arbitrary thing. It's still a capacitive load because the current is leading the voltage. But the R is sort of changing the phase angle of the response, the relationship between the current and the voltage. See these little these little voltmeters kind of going back and forth. So that's not a bad animation to kind of chew on while we're doing these things. Well, we have one more example, example 10. And here we have this thing about sinusoidal steady state. One thing I haven't really mentioned, by the way, and it kind of gets overlooked, we went straight to the sinusoidal steady state. And I should point this out. When you come back to the original differential equation thing here, if you want to get the actual solution to this thing, the actual solution has two parts. Just like when we had the step response for a first order circuit, it has two parts. It has the natural response plus the final value kind of thing, kind of worked in there. So the total solution is the natural response plus the steady state. Now, the natural response is the same natural response that we developed for second order circuits. In this case, it's a second order circuit, right? Meaning that the natural response could be, whatever initial value is, if it's 0, whatever. It could be something like that, where it's oscillating. It could just be, going down like that, something like that. And it's a transient, though. After a certain period of time, that thing goes to 0. The natural response always decays to 0. And overlaid on top of that is the steady state response, which is where you're going to have some kind of a sine wave. So like the VO, if your input has some phase angle, your output's going to have, a different gain and a different phase angle. This might be VO. This might be This might be Vn. If that's the input voltage, this might be Vo. And the total solution, you would have to add those two together, the natural response and the steady state response. But we're normally not interested in that because after like a few milliseconds, you're just going to see the steady state response anyway. This transient just dies out. The reason I'm actually mentioning this now is because I've given a test before, and this is actually, it's pretty sad, but you know, this is how confusing it gets. We're talking about the steady state response. And notice the key word, you might want to just circle this, the sinusoidal steady state. The reason I mention that is because I've had tests where I want you to find the steady state voltage on this thing, and on the final exam, somebody doesn't know what steady state means. It's terrible. We need to have a vocabulary quiz. I think I'll have to make one. Maybe I'll do that somehow before this final exam. Maybe that would be a good review. There's all these keywords. You definitely should know these things. And we don't because we're so busy trying to solve these things. We don't know what the meaning is. So sinusoidal steady state, what does that mean? I just told you. What does that mean? Anyone can paraphrase that? Brian, what did I just talk about for the last 5 minutes? What does sinusoidal steady mean? Sinusoidal steady state mean? Can't even pronounce it. It's a tongue twister. Okay, everybody say sinusoidal steady state 10 times. Sinusoidal steady state. Sinusoidal steady state. Okay, and what does sinusoidal steady state mean? Oh, forgot already. Right? It's only going to show up on the test when I have it as a test question. Who can paraphrase what I just said? Should I say it again?
Sure.
Okay. So the sinusoidal steady state is the response after the transient has died off. The natural response, the natural response happens because you switch something on, right? And if we have this voltage source and it was like off at T0, even if it's a sinusoidal voltage source, right, and you turn it on, you're still going to have a natural response for that thing turned on, right? And that thing creates a transient. The natural response dies out, though, over time because there's an e to the minus t over tau affecting it somehow, right? But after that thing dies out, you're still hitting it with a sinusoid. The sinusoid keeps going because as long as you keep your source on, and eventually you get into the steady state. Steady state is long after that step response, the natural response has died out, right? You've got the sinusoidal steady state.
This is just when there's no power increase or decrease. It's just when everything's going back to the natural.
Everything. So the sinusoidal steady state is for t much greater than 0. We'll put 2 arrows there. So SSS means or implies t is much greater than 0, meaning the natural response has died out. We don't even find the natural response for these circuits. We're just looking for, we only have the sinusoidal response.
The natural response is when the energy that's provided by
whatever initial conditions there were. Mm-hmm.
So when that, I guess in example number 10, when the capacitor pulses out or releases its energy, and the graph will spike. So the SSS is when it kind of calms down and just
yeah. So if there was a switch here where we just switched on this thing, and maybe the capacitor had initially 10 volts on it, right? And we closed the switch to a sinusoidal source at T0, right? Well, you have to actually do the natural response, which would be the capacitor losing whatever voltage it had, or whatever was going on in the circuit initially, is going to decay. It's either going to do something like that, or it's going to do something like that, right? Eventually that transient goes to 0, though. But the true response, the total response, would be the sinusoidal steady state plus the natural response. And the sinusoidal steady state is going to be something like that, right? And you add those two together, and what you would have is some weird squiggle at the beginning where you would have some, you would see that transient dying out because it's added to the sine wave. But then after that dies out, you've just got a sine wave. So that's really what's happening, and my presentation doesn't really emphasize that enough. But we don't really care at this point because, Those transients are interesting, but they only last for a fraction of a second, and they're gone. In general, we're going to have the steady state solution is what we're going to be seeing. When you measure these things with a scope, you're just going to be seeing the steady state solution. Well, I hope that somehow clarifies things.
I'm trying to think of the analogy in my head that works, but I'm stuck.
Yeah. Well, let's do another problem, and then maybe we'll get another analogy after that. So here is the VG that we're hitting this with, 64 cosine of 8,000 t. And we're asked to find out what the sinusoidal steady state is for VO. And it's not a very complicated circuit. It's just a resistor, inductor, and a capacitor. It is a second-order circuit. But we're going to have to find the ZCs, the ZLs. That's the first step, is we're just going to convert this whole thing into the complex plane. So ZC is minus J over 8,000, which is omega, and C, which is nanofarads. This is a really small capacitor, smaller than anything in our kits, 31.25 times 10 to the minus 9. That's a nanofarad. And working that out, you get that ZC equals minus, that turns out to be minus 4,000 J, apparently. Step 2, we're going to find ZL, which is J times 8,000 times 0.5, half a Henry. And ZL is going to then be plus 4,000 J. Interestingly enough, they are the same. And we're going to take the phasor transform of VG to get phasor VG, right? And the phasor transform of VG is going to be what? This is an easy one. 64. And if you want to make it look like a phasor, you could say it has an angle of 0. But that really just means 64. And we're asked to find what VO is. So again, closing your eyes for a second and imagining that that the inductor and the capacitor have been replaced by resistors and the voltage source has been replaced by a DC source, how would you find VO?
Last time to close your eyes was voltage divider, so I'm going with that.
So what happened? What you
Every time I say close your eyes, it means voltage divider. Sorry?
What do you do with the VG? It became a what now?
Imagine VG is just a DC source. Imagine the capacitor and the inductor are resistors.
Okay.
And you're asked to find what VO is.
Is that like Thevenin look back kind of deal?
I don't know. How would you find VO? Well, you could do nodal analysis. Yeah, maybe there's a simpler way, though. Is there any merit to Mike's suggestion of voltage divider? Could you use a voltage divider there?
Maybe a biased opinion, but
Sorry, Brian?
biased opinion,
You want a biased opinion?
voltage divider, yes.
Okay. Meaning you're not sure it's true?
I think it is true.
Okay. And how would you express this voltage divider formula? So suppose I am going to do a voltage divider. Not saying it's right or not, but what would the voltage divider formula do? I could write phasor VO, again imagining that phasor VO is just a DC value.
You have your input voltage, whatever
it would be your phasor VG. Let's just keep it as a symbol just to make it easier to look at. How would you?
2 over 2 plus ZZ.
2 over what?
2 plus ZZ.
ZC?
Yeah.
That's a 2. Don't write that yet. Well, that's 2 times ZL. Okay, since we're actually expressing, that's a good point, ZC and ZL are actually in ohms, aren't they? So we could either put it all in kiloohms and just say this is minus 4J kiloohms, or we can put the resistor in ohms. So Anthony said 2,000, don't write that yet either. 2,000 over 2,000 plus ZC. 2,000 times ZL, he said, right? Does that look right? Sorry?
The resistor and ZL are parallel, so you have to solve that resistance, and then it would be that new resistance times.
Let's do an analogy. Suppose this is 3, this is 6, and this is 4, and this is 12 volts. And I want to know what is VO.
It's the same as the voltage drop across 3, right?
It's the same as the voltage drop across C3. So the formula says
4 over 7.
12 times 4 over 7.
No, 3 over 7 on that.
12 times 3 over 7. Okay. Richard, what do you say?
I was saying, wouldn't it be 12 times on the top of these 6 parallel with 3 all over?
12 times 6 parallel with 3 all over.
6 parallel with 3, or whatever you got for that.
Thank you. I like that. You can't forget, right? When you have a parallel combination, the voltage across the 3 ohm is the same as the voltage across the 6 ohm.
So you still have to include that.
You got to make these go. You got to find the parallel resistance. We did that on one homework problem. We did that on some test questions. Those things happen. They come up all the time. So you have to combine that, and 3 in parallel with 6 is just 2, right? 3 times 6 over 3 plus 6. So that's the analogy, right? And so if you're ever confused about how to proceed, you might actually find it easier to look at if you just change those to resistors initially, because you might have some issues just visualizing those things. So if I'm going to write out the formula, I might think of this thing as a Z parallel. We'll get to that later. But if I knew what the Z parallel was, the formula would say it's VG times Z parallel. I'm trying to get the voltage across this parallel combination, right, over Z parallel plus ZL, which is the series combination of those two. Does that make sense?
Why isn't it ZZ?
Thank you. It's ZC.
So we're going to have to go back.
I know. Do another slide. Here's a capacitor. Here's an inductor. We don't have time. We only have 5 minutes. So Z parallel over Z parallel plus ZC. Okay. Now we have to find what Z parallel is. Well, Z parallel is going to be 2,000 times 4,000 J. It would have been easier to do this in terms of kiloohms, but I'm going to put a lot of zeros in there. It's 2,000 times 4,000 J, because that's ZL, over 2,000 plus 4,000 J, which is 1,600 plus 800 J. Okay, and so that means VO think I'm running out of room here. I'm going to do it up here. So VO, phasor VO, equals Z parallel, so 1600 plus 800J over Z parallel plus ZC, so 1600 plus 800J minus 4000J times VG. And if you do that math, you'll find, lo and behold, it's interesting, this whole thing reduces to just a half a J. Doesn't seem right, does it? Why don't you pull out your calculator and see if you can get that? I think it's right, but you have to try this. You need practice doing these things so you can trust your answers. And we're multiplying that times 64 angle 0. And that's a 90-degree phase shift, that 1/2 J. So that's the same thing as saying, it's the 1/2 of 64, so that's 32J.
It is just 1/2 pi.
Good. You got it? Awesome. You should all be able to do that on your calculators, so that if you're doing your calculators, using your calculators for this, you can do that. So it's 32J, but of course we know that J is 32 times e to the J 90, right? So that's the same thing as 32 angle 90. Therefore, doing the inverse phasor transform, so we're going to do the inverse phasor transform of this thing. So inverse, so this is basically, VO. So we're going to take the inverse phasor transform. They sometimes do this with a big P to the -1 of VO. Implies that VO of T equals 32 cosine of 8000T plus 90. Okay, questions?
The cosine 8000T, that just comes straight from the prompt, right? The VG.
Yes, that's the omega. Good question. So where does that 8000T come from? Because that was our original omega. And we throw out omega when we use omega to find ZC and ZL, but then we throw it away, and it doesn't come back until we do the inverse phasor transform.
Omega never changes?
No, it stays the same. It has to stay the same for these things, yeah. Omega never changes. I was going to show you some additional, if you want to amuse yourself, there are some additional animations. Some of which are pretty cool. I've linked them down below here, I think, in circuit theory animations. And I apologize for not showing these earlier, because these are nice conceptual helps. This is showing you the AC response of a capacitor. And still got all this Java things. Yes. What's interesting about AC circuits that's different from DC circuits is that the electrons are not flowing continuously, right? They're not actually even traveling from A to B anymore. They're actually moving a little bit to the right, then they're moving a little bit to the left. Isn't that cool?
How do you find all these animations?
Well, there's this one site I found years ago. It's called falstad.com. And
Are they on the website?
yeah, they're linked at the bottom here called
Did you guys check the box something back and forth? It's like
Circuit Theory Animations.
brain part.
Yeah, I got a lot behind
There's a ton, and what's another good one? Let's see, for AC circuits. Do you want to see any other one? Thevenin's theorem. Oh, let's see how they do Thevenin's theorem. Oh, that's pretty funny. Look at that. Here's Thevenin's theorem with AC circuits.
Someone playing a complex game of Pac-Man.
Yeah, isn't that hilarious? And what's interesting is you can see all the different behaviors in the different parts of the circuit locally are quite a bit different than the large-scale behavior, aren't they? But what they're showing is this whole circuit has the same behavior from the source's point of view as this little circuit right here.
Like the little portion, some are moving forward, but slightly back, but more so forward.
Yeah, that's beautiful, isn't it?
Yeah.
That's almost a work of art.
What makes some of them go faster than others? Just like you see that triangle.
It would be the resistor values, right?
Yeah.
The speed is sort of dependent upon the voltage difference across them. And the capacitors, I guess are these batteries? That's a battery, I guess.
Because that triangle there is humming, but some of them are just.
These are, I think this is a DC source. I think that's what these are saying. These are DC sources.
What about that bottom guy right there?
You mean this guy?
Yeah, that's also good.
Yeah, so that would be
It's like faster in one direction.
a voltage. Yeah, it's biasing things, isn't it? Because there is a net flow to the currents, right? There actually are flowing to the left or counterclockwise, aren't they? That's because that's a DC source. It's driving it, but then this guy is occasionally pushing it back the other way. So you're hooking up an AC source to a DC source, which we don't normally do. And this is fun. You can change the current speed.
Can you? Oh wow! Can you
Get
like,
epilepsy.
highlight one? I guess what electron and see it go around?
That would be fun, but you have to track it with your eyes. So tracking this one, you can see it's definitely making a net transition counterclockwise.
Seems like the one on the bottom middle isn't actually doing much. The capacitor in the bottom middle.
It's actually a voltage. These are DC sources, I think. Yeah, these are not capacitors. Are there AC? Impedances of the same magnitude. Let's see what that looks like. So these are, I guess, the resistor and the capacitor and the inductor have the same.
Oh, graph all three.
The magnitude has the same, but one's inductive, one's capacitive, and one's resistive. Yeah. I'll take that. Thank you. Cool.
I forgot to mention, I'm not going to be here tomorrow because I'm going to orientation
Okay.
in San Jose. So,
All right.
And I remember you said we had a quiz.
Yeah, there will be a quiz tomorrow.
Can
So you can do it online.
online?
Have you done it even be online before?
No.
Have you logged into FPC Online yet?
Yes.
Okay. So you'll go to the class site and there'll be something, it'll say quiz.
Okay.
It'll be quiz 4. Somebody named Ernesto tried to do quiz 2 when he was supposed to do quiz 3,
Mm-hmm.
and he emailed me like 20 minutes before the quiz ended saying it won't let me do the quiz. I'm like, well, you got to do quiz 3, not quiz 2. But it was too late, so I had to hand him the quiz on paper later, which is annoying.
Okay.
So make sure it's quiz 4. Yeah. Question?
Yeah, I just want to talk to you about the test. Since
Okay.
it's on Friday,